now consider the quadratic equation az squared plus bz plus c is 0, where a, b, c are real numbers and a is non-zero. So if we know, this has two roots over the complex numbers. They might be the same, but still it has two roots. Possibly they're the same root, in which case we have a repeated root. Let's call the roots alpha and beta, which are complex numbers. So if we take our equation, and we know a is non-zero, so let's divide by z, which makes this a monic polynomial. Monic just means the leading coefficient. In this case, the coefficient of z squared is 1. Called a monic polynomial. That's not really important, but we've got this, and we know the roots of this are alpha and beta. So we know this should factorize as z minus alpha times z minus beta. And now let's expand this. We're going to get z squared minus alpha plus beta lots of z plus alpha beta is 0. And then if we compare this equation star with this equation dagger, we can see that if we equate the z coefficients, we have b over a equals minus alpha minus beta, and if we equate the constants, we have c over a equals alpha beta. So another way, so these two equations here are quite useful. The reason they're useful is if you want to do something like, in this example, we want to find the equation of a quadratic polynomial with real coefficients that has 5 minus 4i as a root. We know that if 5 minus 4i is a root, then by the complex conjugate root theorem, we also have that 5 plus 4i is a root. And it's a quadratic, so it can have only two roots over c, but most two roots. So we know the roots are 5 plus 4i and 5 minus i, so the quadratic must factorize. By the factor theorem, it must be either z minus 5 minus 4i times z minus 5 plus 4i equals 0, or any multiple of this. Sorry, not equal to 0. This is the polynomial, or any multiple of this is also valid. So then to find the polynomial, we just need to expand the brackets. So z times z is z squared, and then to work out the z coefficient, we're going to have minus all of 5 minus 4i times z, and minus 5 plus 4i times z. So if we add those together, we're going to get minus 10z. And then we need to work out the constant term, so that's going to be 5 minus 4i times 5 plus 4i, which is 25 minus 16i squared, and I squared is minus 1, so that's going to be plus 41. So that's the answer. So consider this corollary. A corollary is a result that follows from a theorem, or that follows from another result. And our corollary says every cubic equation with real coefficients has a real root. So why is this true? Well, we know by the previous theorem, the complex conjugate root theorem, complex roots occur in conjugate pairs. So there must be an even number of complex root of non-real roots, rather. So we know there are an even number of non-real roots, But there's an important theorem called the fundamental theorem of algebra. So just to tell you quickly what that says, it says every non-constant polynomial of degree n, where the highest power of z is n, has n roots over c, counted with multiplicity. So just a sort of hand-wavy version of that is to say every polynomial with real coefficients, so this is a way of writing that, of degree n has n roots over c, counted with multiplicity. So every cubic has 3 roots over the complex numbers. And we know there are an even number of non-real roots. So a cubic, by the fundamental theorem of algebra, a cubic has 3 roots over c, counted with multiplicity, which just means we might have a repeated root or a triple root. A double or triple root, but we know there are 3 roots, and an even number of them are complex. So, are non-real. So there must be at least 1 real root, because there couldn't be only 3 non-real roots. There'd have to be either 2 or 4 or 0, and there can't be 4 because it only has 3 by the fundamental theorem of algebra. So there must be, therefore, at least 1 of the 3 roots must be real. Okay, so we don't need to know that for the exam, but I just thought that's quite nice to share proof that every cubic with real coefficients has a real root. And the same argument can also be extended to any polynomial of odd degree, where the highest power of z is odd. Okay, so let's now turn to an example. In the next example, we're given that -1 is a root of z cubed minus z squared plus 3z plus k, where k is a real constant, and we're asked to find the other 2 roots of the equation. So firstly, k is a number we can work out, because we know -1 is a root. So if we substitute -1 into the left-hand side, we're going to get -1 cubed minus -1 squared plus 3 times -1 plus k equals 0. And if we rearrange this, we've got -1, -1, minus 3, so -5 plus k equals 0. So k is plus 5. So we found k. Now we need to find the other 2 roots. Well, by the factor theorem, we know -1 is a root, so z minus -1, or z plus 1, is a factor of this cubic polynomial. So we can now factorize it. So to work out the other factor, the quadratic factor, either we can do polynomial long division, we can do this cubic here divided by z plus 1, or we can attempt to factorize. So in order to make 1z cubed, we're going to need z squared. In order to make a constant term of plus 5, we're going to need plus 5 here. And then we just have to work out this z coefficient in the middle. So in order to make minus z squared here, we already have 1z squared. We need to get minus 1z squared. So we need to take away another 2z squared. Because the only other way to make z squared is this z times this z term here. So this is how it factorizes. So therefore the other 2 roots are going to be the roots of this bracket equal to 0. Z squared minus 2z plus 5 equals 0. So we need to solve this. So either we could use the formula or complete the square. Let's do it this time using the formula. So we have z is 2 plus minus the root of minus 2 all squared, which is 4, minus 4 times 5 times 1 all over 2 times 1, which is 1 plus minus, inside the square root, that's minus 16 over 2, and then root of minus 16 is 4i. So this is 1 plus minus 2i. So these are the other two roots of the equation. So we have this equation here, and we're given that 3 plus I is a root of 2z to the 4 minus 3z cubed minus 39z squared plus 120z minus 50 equals 0, and we're asked to solve this equation completely. So first of all, by the complex conjugate root theorem, we also know that 3 minus I is a root, because complex roots occur in conjugate pairs. So therefore, by the factor theorem, we know that z minus 3 plus I and z minus 3 minus I are both factors of the quartic polynomial. So their product is also a factor. So let's work out this product. So z times z is z squared, then we get minus 6z, and 3 plus I times 3 minus I is 10, so we're going to get plus 10. So now we know this is a factor of this quartic, so there are a couple of different ways we could do it now. One way is to do long division, to do this quartic divided by this quadratic polynomial. A different way is to attempt to factorize, so that's what we'll do now. So if we try to write this quartic as the product of this with another quadratic factor. So in order to make 2z to the power 4, we need 2z squared. In order to make minus 50, we need minus 5. And then in order to make 3z cubed, we already have minus 12z cubed here, so we need another 9z cubed. And we get that from adding 9z. So therefore, to solve the equation completely, if we solve the first bracket equal to 0, it gives us the roots 3 plus minus I. And if we solve this equal to 0, I think this factorizes. Because if we have plus 5 here and minus 1, we've got z is a half, or minus 5. So therefore the four solutions are a half, minus 5, and 3 plus or minus I.